All right, it's 2 minutes after 12 now. So we'll get the webinar started. So welcome everybody to this Innovation Showcase Winter Series with the University of Guelph entitled Advancing Bedrock Groundwater Monitoring at the Energy, Environment and Water Interface. My name is Robert Nyman. I'm the Manager of Partnerships and Programs at the Ontario Water Consortium. The Ontario Water Consortium is Ontario's only sector support organization dedicated solely to water innovation. We bring together researchers, companies, municipalities, and governments to drive collaborative R&D, pilot testing, and real-world technology adoption. We help bridge the gap between research and market-ready innovation. And while there are many innovation organizations across Canada, none are focused specifically and exclusively on water like OWC is. OWC's collaborative model delivers measurable results. Over the past decade, we've helped mobilize over $90 million in project funding, $90 million in project funding, supported or created more than 350 industry jobs and advanced nearly 80 water technology projects. We've partnered with more than 100 academic researchers and helped build infrastructure, including wastewater test beds in London and Guelph. We do this by connecting innovators with adopters and aligning the right funding, partnerships, and support to move solutions forward. Before introducing today's webinar, we also hope you'll join us again for our final winter webinar of this series. On February 26th, Toronto Metropolitan University will present plant-wide modeling approaches for wastewater treatment plants, highlighting diagnostic tools for managing fugitive methane emissions. I will drop the registration link in the chat in a moment. All sessions are free to join, and please also note the QR code here that you can use to subscribe to the OWC newsletter. Now, I'm very pleased to introduce Dr. Beth Parker, professor in the School of Engineering at the University of Guelph, to begin today's webinar. Dr. Parker will provide an overview of the integrated tools and workflows her team has developed to characterize fractured bedrock aquifer flow systems, drawing on insights from the City of Guelph's source water protection initiatives. Following Dr. Parker, we will hear from Dr. Ferdinando Manna, assistant professor in the School of Engineering and principal investigator at Morwick G360 Groundwater Research Institute, who will examine bedrock aquifer vulnerability associated with low temperature geothermal operations and the monitoring strategies needed to support responsible subsurface energy development. Beth, the floor is yours.
Okay.
I will stop sharing on my end.
Okay. Have my slides shown up?
Perfect.
Okay, well, good afternoon, everyone. Where I sit, it's still morning. I'm here in Colorado in the US at a field site, but happy to join you all and share some of the work that we've been doing at the University of Guelph Groundwater Institute. It's our two parts are essentially joined, so I think we'll be entertaining questions at the very end of both of our talks here. All right. Are the slides advancing?
I can still see the first slide.
I guess I'll do it manually here. Before I get started.
It worked now. I can see the second one now. Can everybody else see the second?
Yeah.
Yes.
Okay, before I get started, I simply wanted to introduce the style of the group that is involved in this field-based research program that I've developed at the University of Guelph and previously at the University of Waterloo before I moved to Guelph. We're field-focused with our innovation and intentionally trying to develop high-resolution methods that better inform the characteristics of our bedrock aquifers. And in that venture, we're trying to better understand contaminant behavior, as well as the complexity of groundwater flow systems in bedrock systems, and identify and quantify the processes using these new data sets, combined with conventional data sets. Our motivation is so that we can better forecast the future conditions, predicting risk to receptors, as well as remediation designs that are more successful. And so there's a large team of staff and students that are engaged in that work. To get in the mood, I've got some outcrop photos of different fracture networks and different rock types. And what's notable here is that the fracture network characteristics are quite variable by rock type, as well as spatially variable within a rock type. And that's what makes these fractured rock aquifers complex to study and brings a certain intensity in terms of the investigation work. And in Canada, we have mostly fractured rock aquifers that we rely upon, as indicated here in this report in 2005. So some outcrops give us a chance to see seeps or icicles forming at these outcrops, and that gives us a strong sense of the variability of the fracture network connectivity and openings, and lends itself to understanding that these fractured rock aquifers are quite complex. If we were to excavate away on this outcrop 10 meters or 20 meters away, we might see the distribution of the transmissive zones quite different from what we see here. And that's because fracture openings are variable along the fracture plane. And the way that fractures are connected to other fractures is quite variable as well. Our view of fractures in our hydrogeologic investigations usually come from boreholes. And so we're gleaning insights either from core or from geophysical logs that give us a visual impression of these fractures and infer whether they're hydraulically active or not. And what we're working toward is perhaps better resolution methods for perhaps better informing those interpretations that we have been traditionally collecting. Why does it matter how many fractures and so on are active? We'll get to that here in the next slide, but we're very dependent on estimating average linear groundwater velocities as a way of predicting the rate a plume might migrate through a system. And so we use Darcy's law, similar to how we use it in porous media, by dividing by the effective or advective porosity. And in fractured bedrock systems, that's dominated by the presence of these fractures. Fracture porosity is determined by apertures and number of fractures, and so you can appreciate where that number must be derived from, but very few numbers are reported in the literature, but perhaps important to these fractured rock investigations. But when we get to contaminant transport, the importance of the number of fractures and their aperture and connectedness is a critical feature. And I'm showing that here in this slide where we have two fracture network realizations in a discrete fracture network matrix model. The dense network on the left has many more fractures versus the sparse network, but they both have the same bulk hydraulic conductivity. That means the volumetric flow through this domain is equal in these two systems. So it really doesn't have an impact in terms of volumetric flows or water supply, but it matters a lot with the transport. So on the bottom two images, we actually have TCE as a solute transporting in the groundwater, and the source of that TCE is in the upper left-hand boundary, kind of seeing where those high concentration zones are emanating into the system. And so the dense network has a much more strongly attenuated plume because of the increased surface area for diffusion into the matrix or the pores in the matrix between the fractures. And the attenuation of the concentrations is much stronger in the left-hand side compared to the right. So what you can see on the right, the plume has migrated all the way off the 1,000 meter long domain, and we even have very high concentrations on that down gradient extent. So in contaminant transport, we realize that the number and nature of this fracture network is key. So as hydrogeologists building conceptual site models that are perhaps predictive of some of the decisions that we're needing to make, we need to think about the nature of the problem at multiple scales. Starting at the top, we have a multi-layered aquifer aquitard system, a three-dimensional groundwater flow system in a steady state context that's important for us to understand. And we've got a high resolution vertical profile of hydraulic head that helps us to see where vertical hydraulic conductivity occurs or where head loss occurs to help inform the position of those aquitards. And you can see that the flow paths are actually refracted through those aquitards and may be shorter or longer depending on where that release might have occurred in the system. At the intermediate scale, we're drilling boreholes and trying to collect data to inform the position of the contaminants or delineation. We're also informing our monitoring system to see how that contaminant plume evolves over time or attenuates within a contaminated zone and never reaches a receptor. But the data we collect at this plume scale is hopefully sufficiently resolved in space and time to help us understand the processes that are dominating the plume behavior. So whether it's the advection diffusion interaction, the importance of sorption, or even degradation reactions, we're trying to elucidate that at the finer scale, smaller than the plume scale. And all of that is brought together in our conceptual model framework to make the decisions. So in the hydrogeologic manner, we're drilling these boreholes and we're able to collect one-dimensional data sets, and we think of that spatial data as profile data. We can get hydraulic data in profile, such as head or hydraulic conductivity, and we can also use naturally occurring or contaminants with concentration with depth profiles as well, and combine that data together to inform our system. Sorry, I get confused with the old style of moving forward and not. The important thing here is hydraulic data can help inform where the position and thickness of our aquitards, and then concentration or chemical data might better inform where the high mass flux zones are, perhaps the most important parts of the contaminant plume that are creating vulnerability to various receptors. So we're in the business here of putting our boreholes to maximum use. And what we've been emphasizing in the golden spike approach is to collect continuous core to give us key insights on the geology and the presence of fractures and the matrix properties. But we can also subsample that core and send samples to the laboratory for physical, chemical, and even microbial characterization. And so we have been emphasizing that element in our workflow. After we've cored the hole and developed the hole, we like to use a series of geophysical tools, kind of standard in the Bedrock characterization business. But there's also a number of hydrophysical logging tools that are coming to the fore, and innovations in sensor technologies that I'd like to emphasize or point out today that we've also been heavily using in our workflow. At the end of the day, these boreholes are put to use by instrumenting with a permanent type monitoring system. So we can use traditional conventional wells, or more appropriately, think about multiple monitoring intervals separated by reliable seals, and we call those multi-level systems. So this is a slide showing us working at the Fractured Rock Observatory or the city of Guelph. We can see segments of core throughout the lithostratigraphic units. You can see lots of variability observed in these core photographs that are stacked here on the right-hand side. In the field, we've got staff and students working together to collect the core logs, and we try to emphasize not only the primary porosity and lithology features, the color, mineralogy, and so on, cementation, but we're also interested in the fracture features, their occurrence, their orientation, and so on. And that helps us to build the framework that we're building in terms of our conceptual site model. I'd like to just emphasize here that to do this efficiently and consistently amongst staff and students that perhaps come and go at these field sites or working across field sites, we've been developing graphical logging procedures that was recently published by one of my students, Jesse Meyer, and colleagues. And this is just a template that we go to the field with, pre-prepared, that allows us to quickly capture the details and in a fine spatial scale and kind of observe the qualities or characteristics of the core with depth at a glance. It also allows us to convert these data into a database and use these logs in a much more efficient manner going forward. Working in the borehole, we have to recognize that the borehole itself becomes a conduit cross-connecting the natural connected fracture network. And we rely on this. Historically, over the past decades, we've used open hole temperature and electrical conductivity logging to show perhaps what the most transmissive features are in a particular depth interval. But it becomes an issue of concern when we're interested in understanding the natural gradient conditions and wanting to make sure that our borehole doesn't exacerbate contaminant mobility in the subsurface. So back in the 90s, when the flute technology was being advanced, I was working with Carl Keller, and we quickly converted his multi-level into a temporary borehole seal. So it's a flexible fabric liner that's urethane coated to make it watertight. And we can use these prefabricated packers, essentially. They arrive at a site on a reel, and we can invert these liners into the borehole and inflate them with water and temporarily seal the borehole. And after we realized how successful that could be, we got to using our imagination on how we could get more from these sealed boreholes. So now I'd like to convert our attention here to some of the sensors we've been using in these boreholes under sealed conditions. So what I'm showing you here are two types of sensors. On the left, we have depth discrete sensors, which can be for pressure, temperature, or electrical conductivity. And we can use these self-contained transducers essentially to collect data at depth discrete intervals sealed in between with this flexible liner that's schematically shown here in the center image. Alternative to these point sensors, we can use a fiber optic cable, and we can deploy that cable behind the liner, coupling it up against the open bedrock borehole wall, and then use distributed temperature sensing as a modern tool for evaluating active groundwater flow and the variability of that flow with depth in the system. A couple of field shots here where we're putting sensors down the borehole on a string. These are the self-contained depth discrete sensors on the left, and then putting the flute liner in the borehole after that string has had a chance to essentially equilibrate and capture some open hole conditions. We're sealing that in place. First, I thought I would start with active distributed temperature sensing, which we invented at the University of Guelph with my team. The cable is shown in a photograph on the right-hand side. We have the fiber optic sensors coupled with copper heating wires, and that allows us to add heat continuously along the length of that cable. So if we go to the two cartoons of the vertical boreholes, we can see that we have a blue liner essentially deploying this fiber optic cable along the length of the borehole. We insert the cable first, then the liner behind it. We allow the flow system to equilibrate after that installation, and then we're ready to add heat as part of our heat tracer test. So if we go to image B, we can see that we're adding heat through the copper wires, and the zones that heat up fastest are likely less transmissive or less groundwater flow zones, interspersed with zones that seem to be more difficult to heat, as we show in that schematic. So C shows two temperature profiles, the non-heated ambient temperature profile versus the one where active heating is used, and diagnostically showing where there's transmissivity in the system. Okay, now we can go to the depth discrete deployed sensors. We have the ability to put as many or as few sensors as we might have available in our stockroom. We've been putting up to 30, sometimes 40 of these sensors in boreholes, depending on the open interval, and sealing them in place for a couple of weeks up to several months. We have to remove the liner to remove the sensors to download the data, but that gives us an exceptional amount of insight in the system. So an example borehole at our observatory on campus, we've got core data helping to inform the lithostratigraphy that's starting on the left-hand side of this vertical profile montage. Then we've got natural gamma acoustic televiewer giving us insights in terms of the mineralogy and presence of fractures and variability of the porosity. The columns, two columns that I've highlighted in a red box are the active distributed temperature sensing data. And essentially the apparent thermal conductivity is variable with depth based on our fiber optic cable sensing in that borehole. The columns in between the two red boxes show what we can learn by installing our flute liners and perhaps doing some open hole temperature and conductivity logging. If I move to the hydraulic head profile determined from the temporary deployed sensors, you can see that I've got about 17 sensors here, 14 sensors that give us depth discrete head. And we can see where there's minimal head loss and then zones with their significant head loss, perhaps pointing to the presence of a reduced vertical hydraulic conductivity unit we would think of as an aquitard. The high resolution data from this point to the left is helpful in terms of selecting intervals where we might put a permanent port or monitoring system. A multi-depth monitoring system with up to 7 or 8 ports is common with our applications in the city of Guelph. In terms of what is the golden spike, essentially I'm trying to think holistically about all the tools in our toolkit as hydrogeologists, trying to emphasize the value of core and the insights that come from core and the measurements that can be done on core samples. And then that's all shown in orange. If we move to the blue side of this this flow chart, we can see open hole and lined hole methods for collecting borehole data sets. Collectively, we use those data to design these multi-depth systems that can be very cost-effective approaches for monitoring 4-dimensional flow systems. I want to just make an emphasis here that we use the same toolkit to do characterization, to meet some of the characterization objectives, as well as to inform the design of our monitoring systems. So thinking about explicitly what stage we are in the workflow and our objectives, we're evaluating which tools can do that best. So for example, I might go after a 30 or 40 depth discrete profile of hydraulic head using temporary deploying sensors in the characterization stage, only hoping that I can very carefully select the best depth intervals to do the monitoring stage, possibly with permanent multi-level monitoring systems. And what I'm trying to do is avoid the confusion that comes from long open well screens that are more standard or typical in our profession, at least historically. Essentially, we want to get away from blended hydraulic head and hydraulic conductivity values and or chemistry values, and perhaps get more distinct insights from knowing our monitoring intervals and what they represent in that subsurface condition. So multi-level systems are commercially available. There's about 5 general systems out there that are offered, and many permutations in each of those 5 general categories of multi-levels. And so how to select the right one for the hydrogeologic conditions or objectives of your investigation is something that I think more and more of the profession is getting comfortable with that. When we talk about high resolution, it might be useful to recognize that there's spatial high resolution, there's temporal high resolution or frequency data that's now very useful, and our computational tools are very sophisticated in terms of being able to put those data to use. And then our sensors are continuing to improve in terms of their resolution or sensitivity. So thinking about a water supply aquifer and within the source protection framework that we have in Ontario, I've been working with the City of Guelph since the mid-2000s, bringing some of my contaminant hydrogeology experience from legacy contaminated sites that I'd been working on in the previous decade, and converting them to some of the questions and challenges working in an urban and peri-urban environment like the City of Guelph. So this schematic shows some contaminant plumes in the subsurface that appear to be reasonably well attenuated to varying degrees depending on which contaminant type or where they exist in the system. And we've got some of the conventional wells, conventional nested wells, and then a schematic of multi-depth monitoring wells that all kind of work together to build a fairly sophisticated and robust monitoring network in this system. The City of Guelph is an hour west of Toronto here. It sits on, essentially, we have glacial deposits on top of this Silurian dolostone, with the aquifer units being from the Lockport group dolostone. And we have both the Guelph, the Guelph, the Hermosa, and the Gasport formations providing high quality transmissive water supply. We have the Doline quarry that gives us a view of the Guelph formation and outcrop, and I've got an insert here of the Gasport formation, which is quite distinct in terms of its species composition and characteristics. If we look in a plan view map, we've got two different scales here. On the left, we're seeing the greater Guelph area or the surrounding communities, and all the yellow stars represent golden spike characterization and monitoring locations that have been put in since the mid-1990s. If we zoom into the City of Guelph, you can get a sense of how these are distributed within the city limits. And of course, our fractured rock observatory is near the Hermosa River, essentially in the Arboretum, and that's an OWC facility that is designed for collaboration in our professional community. If we take a look at a single gold star or golden spike location here, we can take a look at some of the insights we gained by doing our high resolution characterization or golden spike approach. So we had core from this cored hole. We also had the natural gamma and acoustic televiewer logs that informed provided the depth discrete information as we're building our insights from left to right in vertical profile. We use ATV to give us our tadpole plots. You can see major, minor, open and closed fractures that are identified there in varying frequency. And then in this particular borehole, we had flowing artesian conditions during the drilling operations that ended up with a significant head drop as we opened up the borehole through the aquitard that we'll talk about here in a second. But essentially, our open hole flow metering was our go-to technology because I had a difficult time using the flute liners in this system. So we decided to go directly to a mini port West Bay multi-level system, which you can see here with the displacement of the packers. And that led us to this hydraulic head profile showing the flowing artesian conditions zone here that's highlighted in this red box, as well as the significant occurrence of these really tight aquitards underlying this flowing artesian condition, and then a very transmissive Gasport aquifer underneath that responds strongly to the pumping of the municipal supply wells. So if we step through time, I've got a view of the flow model that was being developed by the city's consultants, and you can see that there is more detail in the overburden deposits than perhaps is being represented in the layers of fractured rock that was not exceptionally well informed right after the source water protection legislation came to the forefront. So we got all these bedrock formations being shown as laterally continuous with constant thickness. The golden spike approach that we implemented allowed us to be a bit more sophisticated with the variable thickness of these units and how they pinch out, And we hydraulically calibrated those geologic formations. So we're thinking about hydrologic units, not just geologic units in terms of this groundwater flow model. And we were successful at winning NSERC Synergy Award, showing the benefits of our inter-collaboration with the consultants in the city. And that happened in 2003. So with this three-dimensional flow model, we're interested essentially in informing the decisions with regard to source water protection that has to do with managing contaminants in this aquifer and how to ensure protection of that resource. The flow model done by the city is equivalent porous media, but the parameters that we're collecting allow us to go across multiple scales using EPM flow models, DFM flow and transport models for discrete fracture matrix transport simulations, as well as scaling some of those parameters to dual porosity or EPM, depending on what the modeling needs are. And this table emphasizes a strong list of methods here and all the ways in which we collect data to inform these different parameters that are needed with models that are different in their approach. Just to summarize here, we've gone from contaminant transport to flow system relevance here, and we've also pivoted into the space of oil and gas and the concerns around environmental impacts from shale gas development, and then also what Ferdinando Manna is going to talk about today, which is using the subsurface for low temperature geothermal. The premise of all this work is that you can't manage what you don't understand. And I guess just as a highlight here, it's the OWC funding that we got in the late 2000s that helped us to build this 9 borehole monitoring network that's allowed us to be very collaborative. And within the last year, we got some philanthropic funding to open a classroom that supports symposia and workshops to enhance that collaboration. So I think in the same style that OWC is promoting collaboration, we're very much interested in that with any of our partners and so on. So thank you for your attention, and I'll turn it over to Dr. Manna.
Okay, so can you just confirm that you can see the full screen?
We can see the screen, Ferdinando. Maybe you can also turn on your camera, just so we can see your face at the same time.
Sorry.
All good.
Okay, here
Excellent.
I am.
Yep.
Okay, perfect. So I'll take over from here and somehow continue the previous presentation, because I'll present how this golden spike approach can be used to design a monitoring system for a geothermal project, and also how can it be used to inform numerical modeling. So you've probably read on the news recently that geothermal energy is becoming increasingly popular. Like even just myself, in the last 10 days, I've read about 10 big geothermal projects that are being planned or completed across the world. Many universities, many campuses are now relying on geothermal energy for heating and cooling of buildings. So it's really ramping up as a green technology. And we essentially have 2 types of geothermal systems. those that follow under the high temperature geothermal, that rely on naturally high subsurface temperature to produce steam for turbines, and then this gets used to generate electricity. And then we have the low temperature geothermal that are below 150 degrees Celsius. And essentially these systems really just require a stable subsurface temperature. And these systems are used mainly for heating and cooling purposes. And this is what I'll be focusing on. And just to provide a bit more context, essentially the foundation for low temperature geothermal system is the fact that subsurface temperature becomes stable and isolated from seasonal fluctuations at depth. So in the schematic that you see here on the right, you can see that this temperature depth profile, and at a certain depth, in this case is 15 meters, but this is not a fixed depth. The temperature is, and I'm just essentially here, you can see that the temperature is cooler than surface temperature in the summer and warmer than surface temperature in the winter. So with these, based on this property, we can use this stable temperature to exchange heat between surface and subsurface. So the geothermal heat pumps, that's essentially how they work. In the winter, you inject circulated cool water, circulated down in the subsurface. There is a heat exchange, and then warm water is pumped up and is used by the heat pumps for warming, for heating the building. And in the summer, when we need to cool the building, we inject essentially warmer water, and then we bring up cooler water, and this water is circulated for the cooling phase. And there are two ways how these heat exchange occur in the subsurface. We can use closed loop systems, and in these type of systems, essentially the heat exchange fluid circulates in sealed boreholes. So normally with closed loop geothermal systems, we drill multiple boreholes, and the exchange, there are these U-shaped tubes. And here there is the fluid that circulates, and that's where the heat exchange occurs. So with this closed loop system, there is kind of like an isolation between the groundwater and the fluid where the heat exchange occurs. And then in open loop systems, groundwater, these open loop systems require on two boreholes where essentially groundwater is extracted, is used for the heat exchange, and then is reinjected. So there is more interaction between the water and the fluid that is used for the heating and cooling, and the formation water, so the groundwater. But regardless of the system configuration, there are three main impacts that have been reported on related to these types of operations. We have cross connection, so the fact that when we drill a hole, there is a connection between deeper geological units and shallower geological units. There is, of course, a pressure perturbation that we cause, and we can change the flow system. This is specifically true for open loop systems, and heat exchange. So we'll see these 3 points in the next few slides. So the issue of the cross connection is an issue that is well known, especially for oil and gas, or even in the oil and gas sector. So essentially, anytime we drill a hole and then we seal this borehole, there is some potential leakage through the well bore, and these essentially put in connection the freshwater aquifer, which is the shallower aquifer that normally has a better water quality and is part of the active water cycle, with deeper formations that have normally lower quality, higher TDS, so they're more brackish or more saline, depending on how deep we go. So this is the first potential problem. The second problem is that when we have water extraction and reinjection, we can alter the groundwater flow system. So in this schematic here, you can see a very simple cross-section where groundwater flows from left to right, and then we have two boreholes, and this is under natural condition. But then when geothermal occurs, we can have injection, and this injection creates this groundwater mound here, and we have extraction, and normally extraction creates a cone of depression. So the fact that we are altering the shape of the water table here is also having an impact on the groundwater flow direction. You can see the curves, the arrows here, they have opposite directions. The third major impact is the development of the thermal plumes, and this is probably the concept that is discussed the most in the literature. And so one critical question from a groundwater perspective is how large are these plumes? And when it comes to fractured aquifers, we have to remember that, as Beth described, like groundwater flow through bedrock aquifers generally is much faster than in sediments and is controlled by these small, irregularly spaced structures. And in this case, when we're talking about heat, but it's essentially the same for contaminants or solutes, the transport is highly dependent on the fracture network geometry and the matrix characteristics. So that's where the golden spike approach becomes useful, because we need to characterize the flow system and the matrix fracture properties. And if you look closely in this diagram, there are some tools that have been developed that specifically use heat as groundwater tracer, as Beth described. And so the information that we can get from these tools are useful for the characterization of the flow system, but they're also used when it comes to heat transport. And just one example I want to give. In 2020, when they were designing the new Morwick Groundwater Research Center, there was the idea of using open loop geothermal systems as a source of heat, cooling and heating. And at the time, in this specific area, we were lucky enough because nearby there is the Fracture Rock Observatory, where we had 9 boreholes where all the geological and geophysical tools were had been deployed to characterize this very complex aquifer. And and among the different tools that were used, also ADTS was used. So I don't want to repeat what Beth said, but essentially we can get information on where the flow is occurring and how heat transport is occurring in the subsurface. And these are just some examples from from the ADTS data. And so we were essentially able to detect zones of active flow that are indicated here in this thermal conductivity profile. And what we was noticed is that these zones essentially corresponds to areas where we have fractures or dissolution channels. And when we compare all these thermal conductivity profiles from all the 9 boreholes, what you can see that it's easy to detect zones of enhanced flow. And are these zones where we have this light blue. But even within the zones, you can see that there is an extreme variability, and that is because it's probably different fractures contributing to those to the flow in those areas. And even more interesting, when we can track the response at the same depth, so probably along the same fracture, we can see different magnitude of response, and that is probably suggesting that the aperture of these fractures are very variable. So we go from more greater aperture to smaller aperture. So all of these data were used to inform a heat transport model. This was an hydrogeosphere model where we were modeling this open loop system. So we had an injection well and an extraction well, and the flow was, so heat and water was injected through a planar fracture, which is depicted here. And again, this was an open loop system, so the modeling was set up to have 5 months of heating when cool water was injected, followed by 3 months of cooling with injection of warm water. And to answer the question, like how large are these plumes, what we noticed without getting into the detail is that if you look at this near the injection well, the thermal bulb stays very local to the injection interval. So there is very limited transport in the rock matrix or even in the fracture plane. And during the cooling, we did the same. We observed the same behavior. So there was a very local plume, and so in the end, this thermal plume was even going to be smaller than the footprint of the building in this specific case. But why is that? That is because heat transport in the subsurface in fractured rocks is essentially limited by the conduction. So we essentially have 2 main processes: heat that is transported with groundwater along the fractures, but we also have some spreading of heat due to the temperature gradient between the temperature and the low temperature of the matrix. So there is this conduction, very similarly to what occurs in solid transport with matrix diffusion, somehow controls the expansion of the fluids. And I just want to spend the last few minutes to discuss another application, and this is an upcoming project that we have here at the University of Guelph, because the University of Guelph is developing a decarbonization strategy for the campus, and they want to use closed-loop vertical borings to supply heating and cooling. And to satisfy the campus needs, it's estimated that we need 300 boreholes to a depth of 250 meters. So it is not a trivial effort. However, as Beth said, Guelph is the biggest city in Canada relying totally on groundwater as a source of fresh water. And here on the right, you see that we have a sequence of the geologic layers from ground surface to depth, and this is a 250 meters hole that is proposed to be drilled. And the Gaspar Formation is the main supply aquifer. So as a response to this drilling, there is the potential cross connection between deeper water and the supply aquifer, and so this is something that we want to avoid. So we need a perfect sealing. But here we are in a carbonate aquifer, so there might be some dissolution features, and those dissolution features make the sealing challenging. And then the other risk that we have in this area is the fact that there might be some development of thermal plumes, and these thermal plumes will cause changes in hydrochemistry. So the city of Guelph, before implementing the full site geothermal system, required a pilot test. And so we are working with the university to design the best possible characterization and monitoring approach for this geothermal project. So we have developed a phased approach where in the first phase, we're gonna install our monitoring system, which requires essentially of 4 different steps that can follow essentially the golden spike approach. So there is some continuous rock cutting to understand the characteristic, to see the rocks that are in the subsurface, distinguish different geologic formations, and log all the features in the subsurface. There is a second step where we will conduct downhole geophysical and hydrophysical loggings, as Beth described, for matrix and fracture characterization. And in this phase, we can have also some temporary deployments, and these are needed to precisely detect where the aquithards are, because these aquithards, these locate units, are essential to protect our main aquifer. These approach will also be used to understand where we have the zones, the more transmissive zones. And combining all of this information together, we can then decide what depth are we going to monitor, because using these multi-level systems, we can maximize the one hole, having multiple ports and multiple depths where the monitoring will occur. Once we have this monitoring system, this multi-level system in place and installed, we can then determine baseline conditions, so we can collect hydraulic data to have a head profile and again understand where the aquithards are, and we can also determine some hydrochemical conditions. Then we go to the phase 2, where the thermal response test will be drilled, and to 250 meters, there will be this thermal response test where essentially there will be a simulation of injecting heat water in the subsurface. And what happens is that after this has been carried out, you will go back to your monitoring location. You can repeat your hydraulic measurements and the hydrochemistry measurements, and hopefully nothing has changed. Like in this case here, that is hypothetical, which means essentially that we are not disturbing the system from both an hydraulic perspective, but also from the hydrochemical perspective. So concluding, just want to say that in the coming decades, geothermal energy will be one of the most widely deployed low carbon energy technologies. And so the potential impacts to the groundwater systems can be mitigated through appropriate characterization. This is a critical step, and especially for fractured rock, we need specialized tools that are different than those that are used for unconsolidated sediments, and these are needed to design monitoring network, but also to parameterize and constrain numerical models. And the continuous pressure monitoring at multiple depths and the routine hydrochemical sampling could enable an early detection on any possible adverse impact in hydraulic or geochemical conditions. And about the continuous monitoring, real-time telemetry can be a critical component because it can be, it's critical to have an adaptive monitoring framework. And just specifically to the geothermal, I just want to conclude saying that there is this common perception that closed-loop systems represent a lower risk approach because they're, as I described, they are somehow isolated from groundwater. However, they typically require a greater number of boreholes to achieve the same heat exchange capacity as open-loop systems. And so the possibility of cross connection with this technology, the closed-loop system, increases. So we always have to take care. We always have to consider both the energy side of things, but also the vulnerability to the aquifer when we pick the right technology. With this, I'll thank you and I'll take any question, and I hope I wasn't too late.
Thank you very much, Ferdinando and Beth, for your insightful presentations. We now have a few minutes for questions. You can pose your questions either in the chat or use the Q&A function, or you can raise your hand and I can unmute you and you can ask your questions to either Beth or Fernando or both directly. We'll give everybody a minute to sort out their questions, and again, either put them in the chat, the Q&A section, and or raise your hand and I will unmute you. Yeah, we have a question here from John Rathbone. I'm going to unmute you now. 1 second. Should be unmuted, John. Can we hear you? I think you just...
Hello, good afternoon.
Yeah, John.
Hi, great presentations. I'm just curious, I know it's preliminary and you're just getting started here, but do you see a potential pathway to drill closed loop geoexchange systems in a sensitive, a sensitive aquifer region like Guelph? Like, do you think that there will be a possibility of that being an outcome, or do you think that it's going to lead to a continuation of a ban of geoexchange systems in these types of aquifer sensitive areas?
Well, first of all, I might just make a comment how important the source water protection work has been over the last 20 years for advancing a strong knowledge base for the city of Guelph aquitard system with a robust monitoring network, which allows them to identify more or less vulnerable areas where this geothermal technology might be put to use. And I think that's a foundational step that's been put forward here, is looking at those vulnerability areas or less vulnerable areas, which we have a few on campus, and then thinking about how we might use the precautionary principle to move forward with a pilot test and then collect the data that helps us to do the best job possible. But I think in the geothermal world, there's lots of science that's been put forward to improving grouts and using the appropriate grouts. But Nando, that's maybe you want to pick it up from there.
No, I think it's yeah, it's all correct. I mean, there is closed loop geothermal systems that have been used really all over the world in fractured aquifers as well. So I think there is potential to use them here. I mean, and I think it's fair to say that we have probably a better knowledge of the subsurface here in the Guelph area as a result of this research program that has been going on for the last 20 years. And we have developed some very sophisticated tools to better quantify the impacts and even just to better design these systems. So I think there is a pathway moving forward, and there might be it might be a possibility to develop these use this technology even in the area here.
If it's okay, can I ask a follow-up?
Absolutely. Go ahead, John.
What sort of, and again, I'm not going to hold you to it, so please don't feel like you have to be specific, but what sort of timeline do you think we're looking at with regards to deployment of these types of sensor suites and collecting that data and then coming to some level of recommendation or conclusion about, you know, how to move forward with geo-exchange systems, whether it be open loop or closed loop systems in these? And I'm just asking just because we're looking at a 2050 timeline for a lot of communities to decarbonize, and some have even more aggressively made pledges for 2040.
Go ahead.
Well, I'm not sure I have a timeline. I guess the sooner we start some pilot tests and we start monitoring and observing the impacts of these technologies, the sooner we will have some recommendation or even just some guidelines, I guess. I don't know, Beth, if you want to.
No, I mean, our goal, I think, in collaboration with the city, is to advance this pilot study with the University of Guelph campus. They have some new construction planned for dormitories and things like that that are beyond their existing infrastructure. And so this becomes a really cost effective approach for augmenting the campus with the modern green energy solutions that are being thought of here. Anyway, so we're on a timeline to perhaps get something moved forward starting within the next 12 months. And I would guess within a couple of years, things will be in place and data will be coming from that. But I do think we all share this anxiety a little bit in terms of this general goal for carbon neutrality by 2050. Time marches on, whether we
have over 6 million buildings in Canada. So the rate that we're going at is not, you just do the math backwards, right?
Yeah, and from what I understand from colleagues like Brian Beattie and so on, heating and cooling is a major source of our energy consumption, upwards of 65% or so, given our climate that we're managing here. So it seems like we are, well, I think we're moving the future for geosciences and groundwater is more and more multiple uses of our subsurface system for energy, as well as waste repositories and critical minerals extraction and all these things. So I think as a hydrogeologist or a contaminant hydrogeologist, I see that we're well poised to do things a little bit different going forward, bringing the best available tools to reduce the uncertainty and perhaps improve our decision making appropriately, and building in, I suppose, the engineering controls that help us to make it as safe as possible.
Yeah, I just wanted to add that there is lots of technology and lots of progress that has been done in some specific sectors of groundwater, like in the contamination sector. Some of these tools and approaches were used in the contaminant sector, but all of these are transferable across different sectors, and the processes are the same. So I think there is enough knowledge to at least to observe and monitor these the impacts.
Thank you, Beth and Ferdinando. Maybe we have some time for a final question if anybody still has one. We're approaching the end of the hour. Again, if you want to raise your hand or type it into the chat. Any final questions or comments for Beth or Ferdinando? Or both? Doesn't look like it. Thank you both, Beth and Ferdinando, for being here today and your insightful presentations. Of course, any of the participants can get in touch with either OWC to get you in touch with the Morwick G360 Groundwater Research Institute, or you can contact Ferdinando or Beth directly. of course, to discuss more and find out more about the work that they're doing at the Institute. So thank you everyone for being here. Thank you. Special thanks to Ferdinando and Beth for taking the time to present. I wish you a great rest of your afternoon. Thank you.
Yeah, thanks for your attention, everyone.